All right, morning everybody. I'm David Bonney, as Matt kindly introduced me. I'm the lead architect of campaign storage at LANL, a technical lead, as well as enterprise backups. And this morning we're going to be talking about the extensions to MarFS that we've made over the past year, our production experiences so far, and where we're heading in the future. I apologize, I'm a little off my kilter this morning. I woke up to a hotel that had no hot water, so I got a very freezing cold shower. So for those of you who don't know, that MarFS is our So the initial problem we had was that, you know, in the past there's been memory on the HPC systems, the parallel file system that is sized to match memory essentially. So as memory grows, both the bandwidth and the size of the storage system attached to the computer grew to. And then the archive kind of was, you know, the landing zone of everything that was left over at the end. And what happened with Trinity was we went from our biggest machine prior to Trinity was Cielo, which was 240 terabytes of main memory, and that's fairly large. But Trinity jumped that from 240 terabytes to that Gary Grider came up with in the, 5-6 years ago, something like that, was the concept that a hybrid system could be better, in that it'd be more cost-effective for bandwidth and it'd be more cost-effective for capacity to have a new layer in between memory and the parallel file system that could handle those bursts of activity and then slowly drain off to the somewhat slower but still fast parallel file system. And these numbers on the right here are not what the actual numbers are in terms of bandwidth. They're just where we think they'll be in the next few years. Whereas the burst buffer is a handful of terabytes per second or tens of terabytes per second potentially. The parallel file system, we hope, doesn't have to be 1 to 2 terabytes per second anymore. For Trinity, we kind of hedged our bet there, and it actually does do a little bit over a terabyte per second. But the result of that is it's gargantuan. It's 82 petabytes for a parallel file system. And for Lustre, that's huge. And no one wants to manage that system. It's probably one of the less fault-tolerant systems that we've had in terms of file system, just because it's so big. And then what we've done at the same point is that as things drain out of the parallel file system, they're hitting the archive. And the archive, if they get there, they last forever. And then they have this snowball effect where if you stored it once, you store it forever. So we inserted another tier in there between the parallel file system and archive called campaign storage that's meant to hold the 2 years worth of data or so and then be purged. And then whatever the users have decided is the important part of their data, they can then slough off to the archive. And hopefully that is a much smaller portion of data than what they normally would have stored. Because if the parallel file system hadn't been 82 petabytes, for example, we'd be pushing a lot of things more off to the lower tiers. And the bandwidth scales, up and down the stack, and we're trying to keep it cost-effective at each level so that, building an archive to go 100 gigabytes per second, it certainly is possible. Do you want to do it, and do you want to afford to do it? Most likely not. So campaign storage is our insertion into that tier where we'll have maybe tens to hundreds of gigabytes per second of bandwidth with fairly large capacity, but at a cost per bit that's much lower than a parallel file system and a little bit over an archive, but not drastically so. So when we were searching out for a solution for campaign storage, we were trying to figure out what we really needed. the standard parallel file systems are throughput machines, but they're also fairly okay at random I/O if you need to do it. Certainly random writes, N-to-1 writes, things like that are all something that parallel file systems are designed and built to do. But what we don't want is something that has more features than we need. So we tried to trim down that set of requirements. And we didn't do parallel tape because that's, it's hard. It is expensive and it's hard to do. Object storage systems are nice, but users don't know, me being one of them, don't really have a good way of interfacing, and our workflows don't really align with a pure object storage system doing pure REST APIs. And we could have built just a gargantuan POSIX file system, but POSIX, there's a lot to it that we don't necessarily need. If you're just storing things and getting things, and all you want is a familiar interface for that, why would we have to do, random write ordering into a single file and make sure that's correct? It's hard and it's expensive to do it, so why do it? So the other thing we have is a unique problem for now, but I imagine others are getting into as well, is that we have very, very large data sets that dump out of our machines. And with a 2 petabyte machine, we're looking at data sets in a single file range of hundreds of terabytes to a petabyte for one single file. Object storage systems don't handle that very well, and if they do, it's something that you don't really necessarily want to try to do. We also have the opposite problem where we have millions to billions of tiny little files. So Trinity with the Knights Landing side of the machine has millions of cores, and if data sets coming out of the machine have millions of files because they dump a variable or a file per process, you end up with millions and millions of files into a single directory, and that's only going to get worse as the systems grow in terms of number of cores. So we boiled it down to what we really thought we needed. We needed a lot of capacity, and we needed it to be safe so that users could store their data for a year to 2 years, if need be, without having to worry that it was going to be damaged or unrecoverable. Whereas if you put a data set that's this size onto a parallel file system and then just left it for 2 years, sure, it's doable, but it's expensive, and you're wasting your resources trying to maintain the stability of a parallel file system for that long without ever purging, without ever getting rid of old data. And we don't really need IOPS. IOPS are something that is purely for interactive workloads and things like that. If we're just storing things and reading them back, all we need is streaming performance. We don't care about IOPS at all. Random I/O latency of 5 seconds isn't a terrible thing if you're doing thousands of operations per second and they're all big. And we need reasonable bandwidth, and reasonable is defined by the size of the memory, and it's intended to be slotted in somewhere between the speed of the archive, and hopefully not near the speed of the archive, but somewhere between the speed of the archive and the speed of the parallel file system. We're thinking about an order of magnitude makes a bit of sense there. So if you have a terabyte per second parallel file system, you're looking at something around 100 gigabytes per second for campaign storage. And the big thing was that we wanted it to look like a file system to users, even though underneath it's using very different technologies. So MarFS is the melding of the parts of POSIX that we like, we being anybody who's ever used a hierarchical file system, with scaled object storage technology, which we're moving away from doing object storage in terms of the commodity systems you can go buy or the commercial systems, but just the concepts, we're using those underneath MarFS. So one of the things that you have to think about when you're doing object storage versus doing POSIX is that basically we can't support all of POSIX, so we boiled it down to what we need. So what we don't allow on object storage systems is update in place generally. The semantics are totally different. There are no tree structures. Permissions are kind of a foreign concept to most object storage systems. There's namespace scaling certainly is nice when it's flat or if it's within a bucket or something like that with Amazon. But you don't want to put trillions of files into a bucket in an S3 instance, for example. So what we restrict within MarFS is we do not allow update in place, period. You cannot do it. Any file you update is actually completely overwritten. So essentially we don't allow it. We only allow writes through our data movement tools, and in this case it's PF tool, which I'll explain a little bit later. But we don't offer a full interface. It's not full POSIX. You can allow writes through our fuse daemon that we wrote, but that's an administrative decision. It's not something we necessarily have designed to be fast. It's just something to be doable. So if you wanted to pipe a tar file into the MarFS namespace, for example. And what we gain through the above is that we have very nice workloads for the object storage layer, and that we don't do anything that it wasn't intended to do. It was intended to get and put, and that's essentially it. But what we do get from this is we maintain full metadata POSIX access. So you have your trees that you expect to see, and everything works and functions like a regular file system until you either attempt to do something wrong, like write out of order, but you can completely randomly read across the system. Not that you'd want to, but it is possible. So you can run legacy apps that only require read access on top of MarFS without too much issue, other than latency is not something we've designed into the system. So the full stack from MarFS looks somewhat like this. It's a library that has all of our common routines in it. A fused daemon for interactive use, so you can mount it up and look at your files and chown and chmod, do all the normal things that users want to do. We have a parallel file movement tool that calls into that same library to move data. It's an MPI program that runs across multiple nodes, can move data as fast as the file system will go on each side. And then a handful of tools that we built for data management. So we have quotas, trash, and packing files. So what we require is the metadata to be stored in at least one POSIX namespace, and in our case, we're using GPFS. And the data has to be stored in at least one object file system, or I say object file system. So I'll get into it later, sorry. But one thing that makes this key and for efficient use is that small files are the death of object storage systems in terms of bandwidth. They require IOPS. If you want to store 4 kilobyte objects across your object storage system, you're going to be just waiting on the latency of every single put that you're doing, and same thing when you're trying to get the data back. So what we do is we take all of the small little files that users would be wanting to store, say they have 1 million 1 kilobyte files in a directory, what we do is pack them into larger objects and then insert that large object. And in the same token, on the other side of things, with large files, we split them into some manageable chunks. So like, as I said earlier, you don't want to put a petabyte size file into an object storage system. What you want to put into an object storage system is something that it handles well. And it turns out that 1 gigabyte seems to be about right, so that's where we chunk things up now, but it's completely configurable. So one of the things we started out to when we were building the system was we wanted it to be as scalable as possible in every way and have basically a knob you could turn for every single piece of the file system and to be able to run faster or slower or more expensive or less expensive. So one of the things we built into the system was namespace scaling, so that we're never going to have the problem where if you're inserting 1 billion files, you're not limited by the rate that you can insert them. Excuse me. We're trying to get them inserted as fast as the underlying storage can go, and the metadata is just a side effect. So we want to build the metadata out in a way that we're not limited by that. So we have n-way scaling. I have a picture on the next slide. But we have n-way scaling within individual directories of trees. So we can shard within a directory or within a set of trees. Sorry, that's, like I said, cold shower this morning did not wake me up like I expected it to. But within directories we can shard, and across directories we can shard as well. So we end up with a tunable that we can say if you have 10 projects, you could have 10 separate metadata file systems, you get 10 times insertion speeds across them. Or within a directory tree, you can pick a directory and say shard that across 1,000 directories, and that will then run 1,000 times faster potentially. The data movement is purely a function of how much you want to throw at it underneath, building out the network, building out the storage. There are no real limits other than administrative overhead for adding more storage repositories or multiple sets of storage underneath the system. So here's a somewhat hard to read picture of all of that, but essentially this is just showing you that you can have as many projects as you want that can be separate metadata file systems entirely. They can all share or use separate data storage repositories at the bottom layer, and directories themselves can then be sharded across multiple namespaces as well. And the directory sharding is still a work in progress, but the namespace sharding for full projects is in the product today. Sorry about that. Let's try this again. Okay, back to where we were. So for the directory sharding, what we wanted to do was test the harness that we had built. So what we did last fall was we built an MPI test harness for the MarFS design concepts, and then put them on CLO. CLO was our outgoing HPC cluster. It's a little over a petaflop, has 140,000 cores, over 9,000 nodes. And what we wanted to do was, show that as we scale this namespace out, the limitation will be how much money you want to throw at building a metadata system. So I really, really wanted to put 1 trillion files in a single directory, but I crashed the high-speed network, and they decided as an administrative decision they didn't want to spend the time to get the machine back up and running. So that was the last thing that ever ran on Cielo. But we got to 968 billion files in one single directory that were statable. You could do an LS across them if you chose to. I did not. And the big thing was that we almost got 1 billion files per second insertion rate. And this was not cheating. This was not local caching or anything like that. What we had was a client and a server that were completely separate processes within the stack. And they were randomly distributed across the system. And then every single file creation would randomly pick a destination server based on a hash of the file name, so it's not random, and send a single QDEP1 request across the wire, have it create on the local storage, which is just TempFS in this case, and then get a confirmation back, and then move on to the next operation. So this was actually hitting the network with a single, it was a RTT every single time you wanted to create a file. So this is really a testament to how big you could build a system if you really wanted to. Now, I would not suggest building something that's 140,000 way sharding, but it is possible, and we did do it. And the other thing we were looking at doing on one of our smaller clusters, also outgoing, was doing readers as fast as possible and do reader stat as fast as possible. And surprisingly, it was a super linear speed up for the small testing we did, but we need to actually delve into that a little bit further when we build a production version of this. But we got a 400x speed up over 50 nodes for doing reader stats across a single directory with many, many files in it. So this is what we envision a simple MarFS deployment to be. We kind of split up the interactions that users would have with the system between the interactive file transfer agents and the batch file transfer agents. So the interactive agents, they can sit on those machines, they can do all the weird things that users normally do, manipulate their files via the mount point. But then we have dedicated batch systems so that you can move data in and out of the system without being impacted by those users potentially doing bad things on the interactive nodes. You have to have some sort of data repositories, and you have to have some sort of metadata repositories. And we have envisioned using GPFS simply because doing lists across GPFS is very easy. It's easy to do inode scans and say where are all the files in the last 10 hours that have changed. That's very easy to find at GPFS. And the metadata scaling for it's fairly good as well. And this is what a file looks like. If you have a file that's just right in terms of Goldilocks speak, you've got a file that's somewhere between 500 megabytes and 2 gigabytes, or whatever those limits happen to be for whatever storage system you're using. That was what we call a unifile, a file that becomes a singular object. And what we use is on that object, when you're storing it into the file system, there's a stub file that goes into GPFS or into the metadata tree, and then there's an extended attribute that points our libraries at the object storage system or whatever storage system is underneath. It says, here's where the object is, here are its attributes, and this is how you access it. For multi-files, that's a big file that is chunked. We just have a formulaic way of generating the object names, and those get stored into a single XAdder and then expanded on read. So there's no insertion rate or gargantuan XAdder that you need to read, or a list of things that you need to go get when you want to access your file. It's the libraries underneath, read that XAdder, generate all the names, fire out all the work out to the PF tool instances, and the data gets copied. And then the converse of a multi is a packed, which has a singular object with many objects packed within it. And the XAdder just points to the offset within that object. And we also additionally store a manifest of all of the files within a packed object at the tail end of the object so that we can read it back in case we lose the metadata file system. So basic configuration of this system ends up being not too bad. You choose a top-level MarFS mount point. It doesn't actually have to be a mount point. You don't actually need to have the file system mounted to use it. You can do all of your manipulation through PF tool if you wish, but you can't really change metadata permissions or anything like that if you don't have a mount point for it. And then you have a stanza for all the different things that you're going to put into the system. So project A, project B, all that kind of stuff, how they're accessed, what the protection levels are, and then a stanza that describes how you talk to each individual system. So in our case, we initially started out with the Scality Ring product, and we just had a little stanza that said this is how you talk to it, these are the servers hosting it, that sort of thing. There's some things in there for retries and latency and things like that, because you have that concept when you're dealing with object storage systems. And for recoverability, we were trying to be very, very careful. We didn't want to have to build something like this and then find out that our metadata file system crashed and, oh, the last snapshot was from 2 weeks ago, or we don't have one at all because the tape got munched when we went to recall it. So what we tried to build into the system was as much recoverability as possible without compromising the initial goals of bandwidth. So as we're writing files into the system, what we do is we encode into those X adders the object name that we're actually storing encodes the creation time attributes of that file. The original path, UID, GID, mode, times, some of our special extended attributes as well, but they're all encoded into the object name itself. So if everything went wrong, and everything can go wrong as soon as you say it can't, if you lost your entire metadata file system, what you can do is troll through and read all of the object names and essentially rebuild the creation time attributes of the file system, which was a nice warm fuzzy in the back of your mind when you go, I wonder what happens if GPFS just has a bug and it explodes, or our servers get hit by lightning or something like that. As I mentioned before, PFTool is the preferred method for us to move data in and out of the system. It's an MPI program that we've written at Los Alamos for the past decade plus. It's essentially a parallel rsync. And it dynamically load balances across nodes. So if you have 10 nodes and they're all varied hardware, that, doesn't really matter. They will all go as fast as they can. They don't have any synchronicity between the worker processes and the parent process. It just hands out work as needed, and everything goes as fast as it can possibly go. We do have restartability for any point in the system, essentially. So on the object boundaries, we can restart. So if you're writing a petabyte-sized file, you get to 999 terabytes out of a petabyte, and your job crashes. That's not terrible. You just fire it back up, and you might have to redo a couple gigabytes of work, but it's not 999 terabytes you get to copy again. And the other thing is you can read in, you can read in older packed files and repack them and things like that. So it's fairly useful, and it does go as fast as the storage system can go. We tend to actually cause trouble for the storage systems when we do a parallel stat and read dir across and do a tree walk, because if you have the parallelism set too high and completely swamping Lustre, for example, with the tree walk code. So you have to be a little bit careful, but we do have limitations. You can say no more than 10 ranks are able to do the tree walk at the same time to limit the impact to the system. So first production design, Matt alluded to it last year, or from when I presented last year. We were in the process of putting into production middle of last year. And our first design was 22 petabytes of storage, and that was the Scality ring product. We're running 20+4 erasure, and we did do 6 failure domains, which is something that Scality kindly added in for us. So we could limit that 20+4 erasure to be placed within, for every object, to place within 500 drives. So rather than having a +4 over 3,000 drives, we had a +4 over 500 drives, and that seemed like it was a little bit safer in terms of the way the system was designed. It's 48 Dell servers, pretty standard things, running 100 gigabit EDR, and we were running IP over IP because none of these object storage systems, at least when we were building it, supported native InfiniBand. And then we use standard Seagate enclosures with the 8 terabyte archive SMR drives. And if you're not familiar, SMR drives are shingled, and the way you write to them is similar to a regular hard drive, but what happens if you give them a bad workload is they fall off a cliff, and you can get a handful of kilobytes per second out of a hard drive if your workload is small random writes. So that was a little bit of a challenge, but Scality actually coped fairly well with that, surprisingly. There wasn't a whole lot of tuning to be done. We weren't getting anywhere near the full bandwidth of the system, so it tended to write just enough to each drive, and by the time I got back to that drive, the drive had already shuffled the data off to the shingles. We had 6 terabytes of metadata storage, which sounds small, but we don't really need a whole lot because GPFS is fairly efficient at storing metadata. And that was just a triple server setup with, again, EDR. And we were using native RDMA access for that to get latency down. And we triple replicated across them and backed them up every week or so. And then the cluster of the file transfer agents, there were 5 interactive nodes and 25 batch nodes. And they're all fairly, these are all the same hardware, essentially. And it was about 24 gigabytes per second of bandwidth, which was about our initial goal of gigabyte per second per petabyte, which we're going to push a little bit further in the future, but at the time, we wanted to set a modest goal, we thought, at a gigabyte per second per petabyte. So where are we now? over the course of 6 or 8 months, users stored about 2 petabytes of data, which was not what we expected. We expected users to use it a little bit more heavily than they did. So we kind of attribute that to both the fact that our admin team for the parallel file system is great, and they managed to keep the system very, very stable over the course of that time. And we also didn't do much outreach on our part for the users, so they didn't really understand why would they use campaign storage when it has these limitations when I could just use the parallel file system, which in our case, unfortunately, was 82 petabytes. So it was 4 times as big as the system we even gave them. So unfortunately, because of our hedging of our bet on Trinity, there wasn't really a drive for users to push their data off of the parallel file system onto campaign storage. And that's probably going to change in the near future, where we're working more on user outreach. But that whole time, we ran this system with, I say 1.3 people, but really, it was whatever time myself and the other admin on the system could find to keep it going. And thankfully, there wasn't a whole lot to do. It was just monitoring and keeping things running and hardware failures here and there, but it wasn't the end of the world. But in terms of a multi-petabyte file system, if this was Lustre, it would not have been a person and a half trying to keep this thing running and keeping it in production 24/7. It would have been a little bit more of an effort. And I'll talk a little bit more about multi-component repositories. I know that's a foreign concept at this point, but we did recently complete a move from Scality storage off to our own custom-built storage system, which we're calling multi-component storage. And there were a couple things we learned from that. It was a fairly painful process as we eked out bugs that we did not see in our test bed and our development machines as we moved to the full size of the system, which in this case was a 30 petabyte repository. We hit a lot of edge cases that were quite fun to debug, and you'll see why when I tell you how we access the data in a little bit. But one of the things we learned was that you can't ignore any single little error, even if it seems to be completely inane. It actually caused most of our pain, which was, I'll get into that on the next slide. So what we did that we thought was good, our metadata stability and scalability was great. We didn't have any issues related to that whatsoever. The metadata storage by design was faster than we expected the storage system to ever go. So inserting 100,000 files per second into MarFS was trivial. It did not cause any trouble at all. We were completely IO latency bound going into the storage system underneath. User workloads, regardless of their form for the most part, were in the order of 3 to 5 gigabytes per second per user for each of those transfers that they were running. And these transfers ranged anywhere from a user storing 10 gigabytes of source code to 150 terabytes of dump data or visualization data that was fairly nicely formed. And then if users would put multiple transfers in flight, they would get up to that aggregate limit. It would kind of just flatline there. We had pre-scheduled DSTs only. It ran fairly well. For the most part, we didn't have to do a whole lot of TLC. We had one downtime that we did not plan for that was hardware related, but once we got the node fixed and back up and running, we were back to the races. And one of the things that we also attribute to the reason why users didn't really utilize the system a whole lot was we have quotas. What we didn't want was for one user to fire off a job and then we'd come back the next day and find out they used 9 petabytes of our 22. Now, if they had a quota that high, that's fine, but none of them asked for that and none of them did. But what we built into the system from the ground up was the intention that users would not be able to monopolize the system, because any system without a quota, as you all very well know, users will take advantage of anything you give them. So if you give them an inch, they'll take a mile. If you give them an archive that can write at 10 gigabytes per second, they will do that until you're out of tape. And then you just are inserting cache into the system rather than trying to do something useful with it. Especially in an archive case where you're going to get tape, you're not going to get your data back in a reasonable time frame anyway. So we built into the system, and we have a tool that runs every 2 hours, and it only takes about 30 minutes to scan the number of files that are in the system. And as we've scaled up, we've watched the runtime for this, and going from 1 million to 150 million files in the system, the runtime went from 25 minutes to 30 minutes. So it's not growing linearly with the number of files. And as we grow, we're just going to keep monitoring this. And we've built into that tool the ability to split up these namespaces so that when we're doing these inode scans, we can separate it so that user A is on this system being scanned and user B is on this other one. And they should be able to run in parallel at basically double the rate, or however many we're running in parallel at the same time. And what we did wrong, and this I'm standing up before you a little bit ashamed, we missed a couple things in production that, unfortunately, because of the way we built the system, we did lose a little bit of user data. And I stand up here ashamed saying that we built a storage system that lost some data, but it was purely because we missed something early on. there were some daemons in Scality that would crash, that we would not see that they were crashed, but these are the daemons that handled rebuilds for drive failures. And they would just silently fail in the background. And we attribute this to the fact that we took Scality's product and I'll call it a hack. We got it running disklessly, so there was no OS disks in the machines, and in hindsight, I would have rather put hard drives in every machine and boot up a regular OS. But we did do this thing where we got all the Scality nodes running disklessly, and I think the side effect of that was that we missed a log somewhere. And it was not a fatal error. It was something that just kind of silently ran in the background. But if we weren't paying attention, the daemons that handled the rebuilds would crash in the background, and we wouldn't know about it. So out of all the data we stored in the system, we lost 0.003% of it. And that sounds small, but when that's a set of 150 million files you need all of, it's a really big number. So yeah, that was painful. And the other thing that we introduced into the system because we built it diskless was a single point of failure in the logger for Scality. So all the nodes within the system were sending all of their HTTP logs, all their access logs, all of the internal Scality logs to a single box that had a bunch of ZFS storage on it, so we could just troll through the logs and look for things that were wrong. And that was a single point of failure we added into a system that would otherwise have been fairly stable regardless of how many servers we had killed off, up until we exceeded our erasure coding set. So we were doing a 20+4. If we hadn't messed up the system, we would have been able to tolerate 3 or 4 server failures without really any change in access. But because of the way we built this, that one logger box, if it crashed, would take down the entire system. So, like I said, hindsight's 20/20. One of the other things that we didn't really quite expect was that one of the users had, I would call, a very bad form for their data, and it was tens of millions of files in the handful of kilobyte range. And while we did build the system to handle that, we didn't expect to have that many that small. So initially, we were conservative with the way we're doing packing within our data transfer tools, and we were only packing 128 to 1. So that ends up being a couple hundred kilobytes of I/O to a storage system. We are looking at expanding that. We've got it in testing now to do 10,000 to 1. It was just, we didn't want to jump too far too quickly. And like I said, user education, we did not really explain to users why they should be using the system. We explained it to everybody in the outside world, but for some reason we forgot to tell our own users that we really, really wanted them to use this system. But like I said, it was compounded by the fact that we had an 82 petabyte luster that was fairly stable. So what we have now, we deployed it last week. It was the final nail in the coffin for Scality for us, was we built our own storage system that, and like I said, you'd laugh, we're accessing it via NFS, running IP over IB for now. And that is one of the reasons that I say monitoring, and painful. We found all sorts of fun things with NFS running at scale with incast problems and all sorts of stuff on our network. But basically, it's the exact same hardware. We added a JBOD to it, and we're using all of the drives within that JBOD. So 84 of them running ZFS. So it's about 30 petabytes pre-compression. Read speeds are okay. Write speeds are not as good as we would like. We attribute a lot of that to the pain of doing NFS. But that is a temporary solution. We're actively working on building an RDMA, completely native verbs, top to bottom from the client to the storage, that we've benchmarked initially at well over 100 gigabytes per second. Recent enhancements to MarFS stack. We've added a couple things that make it simpler for everyone to add their own new levels of data abstraction. So we have a data abstraction layer, and that's got essentially you have to do put, get, delete. I think we might require stat, I don't remember. But the minimal set of operations needed for doing data access, you can write your own shim to do whatever storage you'd like. So we have one for Amazon S3, we have one for Scality CDMI, we have one for our new multi-component repositories. We have the same thing for the metadata abstraction layer. You can use a key value store if you choose to. We have not built that yet, but it is possible. You just need to write the little shim code that translates all of the different metadata functions into something that your storage can handle. Multi-component repositories, those are our own storage system, essentially, that I will explain in a slide. And then packing in PF tool, like I said, we ran 128 to 1. We're exploring doing 10,000 to 1, just to make sure that those bad user workloads don't impact the performance of the system quite so much. I just went over this. So multi-component repositories. So I do have a talk tomorrow that's going to focus a little bit more on this, but for today, the why is, imagine a system with 20,000 hard drives in it, and you're storing your data with a 20+4 erasure coding. And what we quickly realized, because of the way we're splitting up our data, every object matters. You can't just say this one's not important because it's some user's picture they don't care about from 10 years ago. It could be a chunk of a petabyte-sized file. And if you put a 20+4 erasure and you distribute it over a system with 20,000 hard drives, what happens when you kill 5 hard drives simultaneously? The answer is you lose data. None of the systems in place today can handle widespread instantaneous data loss or hard drive loss. So if you have 30,000 hard drives or 20,000 hard drives or some large number of hard drives and your erasure coding is on the order of plus small number of n, you will lose data if I go out and pull 10 drives and then turn the system on, or 12 drives or whatever exceeds your production level. So what we built was a system that does both a top-level erasure coding, so say a 10+2, something fairly easy to compute, and then it stores them across another set of erasure-coded storage systems. In this case, it's ZFS. So yeah, we like ZFS. We run all of our Lustre file systems on ZFS with the exception of the one on Trinity. We've got a lot of local experience. So what we did was we took all the niceties that you get out of ZFS and we just layered an erasure coding system across the top of that as well. So even though you have a RAID Z3 at your bottom level, you can put a configurable erasure across the top of that as well. So not only do you have protection against local failures, you have protection against system-wide failures. One of the nice aspects of that is that rebuilds essentially always happen at a local level in the bottom layer, and you only have to instantiate these heavyweight, go rebuild an entire petabyte's worth of data in the rack when an entire storage system completely fails, so you've lost more than your protection level at the bottom. And here's a picture of it. Hopefully that looks okay. Yeah. So this is what one of our component looks like, or one of our components look like in our production system is we have, in this set, 12 storage nodes. There are 4 ZFS file systems on each of those storage nodes across that JBOD. It's a 17+3. And then across the top of that, we place our 10+2 parity. So the amount of drives you can lose in this system, if you just shotgun random drives across the system, is unparalleled. But it also takes advantage of the fact that doing 10+2 at the top is easy. That's a fairly easy calculation to do. We're using the Intel storage acceleration library to accelerate that. And at the bottom, it's just building ZFS storage nodes, and many people can do that. That's not a specialty. So we tried to set out to build something that was both simple and complex at the same time, but the parts that are simple are the building of the storage blocks, and the only thing that's complex is the upfront configuration and coding. So looking forward, we were trying to figure out what we could do for longer-term storage. So as I said, this was designed for this 6 months to 2 year time frame. And what if users want to store their data for 10 years or 50 years? And that's starting to sound a little bit like an archive, but it's not really intended to be an archive at this point. We're just trying to come up with better ways to store things on tape. So this is a crude drawing, but it's essentially the same, except that instead of having shingled hard drives for doing the storage, which is what we're using across the stack now, we'd probably use PMR because the workload will be a little bit higher. And as we need to, we can do our same erasure coding, say it's 4+1, 5+1, 10+2, whatever you want to go widthwise on your tape drives. You can write that down to these disk storage nodes, and then we can batch that data out to tape and batch it back in and reinstantiate into the MarFS file system. So what we built here is a way to erase your tape. And so we can use cheap LTO tape that has a higher bit error rate and not have to pay the cost of doing replication, which is painful when you're talking about petabytes worth of data. So yeah, I just described a lot of this here. So what we don't have for any of this so far, this is purely concept stage at this point, we're doing initial testing, is a way to nicely handle this for users. So we're looking at building a batch interface that a user can say, I want to move this data from Lustre or from NFS or wherever into this longer-term MarFS file system and then send it out overnight. So we're not letting users instantiate a tape mount because that is a painful thing to admin. I mean, you could have hundreds of tape drives, and if users are constantly banging on them, not only do you chew up your tapes, but you chew up your robotics and you chew up your tape drives. So we're looking at trying to put it into a more batch-oriented model where users say, I want to move this data from here to here, and we say, okay, fine, tomorrow morning it'll be there. We'll send you an email. And that's what I've got for today. I'm open to any questions, and we do have all this up on GitHub. There is nothing that we will be releasing that will be proprietary. It's all going to be completely open sourced. and is open sourced. And we welcome any contributions from anybody that chooses to. You have to click it on.
Ahmed? Oh, there it goes. Okay. So questions? If you could maybe come to the center, and then I'll give you the mic if you have questions.
I'm curious whether you've looked at correlated failures in drives, especially in ZFS servers, which may be due to things other than disk drive
bugs?
failures, to software failures or odd conditions that might cause banks of correlated failures, and what you guys have thought about doing about that.
Yeah, absolutely. So I'll touch on that more in my talk tomorrow, but that is something that we are concerned about because as drives get more and more complex, especially these shingled hard drives, they have very interesting firmware characteristics, and sometimes you can push them into a weird state that you didn't expect, and you find edge case bugs. And that's something that's very hard to protect against, especially within a single server. So in a perfect world, you'd be buying all of your disks in every different storage server from different vendors, and they'd all have different firmware revisions, and you wouldn't have any of that correlated loss. But unfortunately, that's a hard problem to solve, and I'm not sure that we've solved it with this. We've just kind of tried to mitigate it so that if you catch it early enough, it might not be as much of a problem.
Is any other site using MarFS besides you guys?
So at this point, within the DOE labs, I do not believe that's the case. But there is a presentation next from Peter Brahm, who is commercializing the MarFS software stack. But no, not with, it's just Los Alamos at this point.
So is that where, if someone else wanted to use it, is that where support would come from, is from like the commercial offering?
At this point, we're happy to offer what help we can provide via the GitHub site, but also I do think that Peter plans to do that. I don't see Peter in the audience. Where is he at? I would direct your questions to him.
So do you really envision the future of storage being massive file systems with trillions of files being inserted per second going forward? Or is this a stopgap until we get to a point where we have a better solution?
So I hope not, because I don't want to admin that system either. But we're trying to build something that if the need arises, it could happen. So we're looking out towards our next big system is going to have many petabytes of memory. It'll probably have many, many petabytes of in-system flash or some kind of non-volatile RAM. And perhaps maybe we don't need to buy such a big parallel file system when we do that. So we're building up this stack to be able to handle the combined user workload of pushing all that data in and out of a system that might have 10 million cores or 100 million cores, which might mean 100 million files need to be inserted fairly quickly. So we just wanted to have a little knob that we could turn for each little piece of the system. I hope I don't have to do a trillion file system either.
Can you give an idea of what, you said there was one where the system went down unexpectedly.
Yes.
In a large distributed storage system, I would expect that you might have a lot of nodes go down, but never the whole system down. Can you give an idea of what caused that, everything to go down?
Yeah, so that was the single point of failure we introduced. The logger box crashed. Yeah, normally that wouldn't be an issue, and in this new design with multi-component, it can tolerate. We do allow reading as long as there is so we do checksums through the entire stack, and as long as there's not a checksum error on read, you only need the number of data servers up you need to read it. So if the 10+2 is your top level stripe, you can read it as long as you have 10 servers up. And the same thing for writing. We enforce a +1 on write at this point, but that's completely configurable. So whatever level of reliability you want to tune into the system. But that one failure was caused by the one single point of failure we added into the system. That's why I was blushing. Yeah.
Do things change as you move into these kind of next generation machines in terms of how you use MarFS and goals, et cetera?
What do you mean things change?
I mean, just, you'll have a much, are you anticipating any big differences in your workloads that MarFS will experience?
So I'd like to think we have a fairly good idea of our users' workloads. We weren't expecting the really bad workloads that users had come up with millions and millions of really, really tiny files. But In general, we've designed the system to handle most of that. If somebody comes up with an edge case, we'll try to figure out a way around it. But at this point, the benchmarks we run are probably worse on the system than anything that users have ever exposed it to. What's that? Good question. So, as you might have noticed, when I described all this, it sounds fairly static, right? So what we're working on currently is a consistent hashing that will let us migrate data between different repositories, at least different multi-component repositories. So as we add in new hardware and decommission old hardware, we can just adjust the hash, have it rebalance, and then decommission the old hardware. Yeah, price per bit. So I will say that the price per bit deployed on the floor is just over 4 cents per gigabyte for this system, and that's including all of the FTAs, all of the networking, all of it at this point. So it's very low cost compared to even the cheapest Lustre you can build. And it's a little bit more expensive than an archive, but not horrendously so. Thank you.
Okay, John, you want to go ahead and, John Kachuk? Yeah. Thanks. We're going to, I just have been emailing with Peter Brahm. He got stuck in traffic. So we have a short talk that was going to be done later this afternoon. So we're going to go ahead and let John Kachuk give the short talk, which we've got time for him. John and I are actually old colleagues. I've known him for many years. He's been doing systems work at very large-scale data centers for the last few decades. DOE data centers, including NERSC, also commercial side, Industrial Light and Magic. So John has a lot of experience with really large-scale systems. One of the things he does a lot of is testing new systems. So if you want to just use a VGA, or you could copy here. Yeah, okay. So I'll give a little bit of background as he works this. So we had John speak a couple of years ago on his performance tool, which is called Bringsel. So that tool allows you to kind of develop really varied workloads, file system workloads and test systems. So recently, as part of his work at Seagate, he's been doing large-scale testing of HPC file systems, including Lustre. And so he's been seeing some interesting things with regards to sort of initial state Lustre and performance. And so if we can get his talk going here. I just, yeah, sure, you can just put it up here. Okay, got it. So do you want to stick with, we're going to,
Just use the HDMI interface. This guy here. Hopefully, that will go. Yes, no, maybe, maybe not.
do you have to,
Here.
yeah. Actually, can you put this? I think we need, and then do you need this piece? Get onto a USB key. Do you have a USB key? Do you want to just copy it on there? Well, we could try.
C for a short talk and getting all this stuff set up. By the time we get this done, Peter will be here probably. All right, so I'm with Seagate, and as Matt was alluding to here, this is a very short talk. It's only 8 slides. It's basically a work in progress that we're doing at Seagate, and I'm with the High Performance Computing Group at Seagate, what we refer to as Cloud Storage and Silicon Group. Pardon me. Okay, and there we go. So I'm basically here to talk about a work in progress that we've got going at Seagate within CSSG, which is the effects of fragmentation and capacity on Lustre file system performance. And this is a work in progress. So there's only 8 slides. The analysis for the data that we're collecting should be done by the end of this month, and the full data will be presented at LUG 2017 in Bloomington. But so why are we doing this? What is involved? A little bit of history and background. We'll talk a little bit about focus. We'll talk a little bit about our test environment, the nomenclature methodology, and then we'll talk just a little bit, touch on some of the performance tests that we've been running and the amount of data that we've gathered so far. So why are we doing this? Basically, production realities rarely ever match vendor promises, and I work for a vendor, so I can freely say that. I've also worked at customer sites. So typically, when we get RFPs or RFIs from people, whether that be Department of Energy sites or oil etching, what you ran during your acceptance period. And that depends on both capacity and fragmentation. And the supposition that we have is the fragmentation in Lustre, even at low percentages of utilization, 20, 30, 40%, can make a drastic degree of impact on what you see for end user performance for applications. And the other reason we're doing this is there are, unless, in case it isn't intrinsically obvious, there are relatively drastic shifts coming in storage models and utilization. And by that I mean a lot of what we're doing in storage today is driven by the transition from hard disk drives to all flash array or SSD types of technology. HDDs are starting to mature, they're starting to evolve, they're becoming a lot more focused on cloud services and cloud storage providers. All flash arrays have their own issues regarding lifetime limited write capability and how they respond to different read and write loads. So each storage block device that you might be using, whether that's a solid state device or a spinning disk, has its own different set of challenges. And that has to be factored into file system design and extended use. So a little history and background. Fragmentation as an issue goes way back. If you look at the file systems literature from computer science, I've got papers that go back to the late 80s, early 90s, discussing file system fragmentation. Despite some of the work that's been done in the past, a standardized way to generate test file system fragmentation doesn't generally exist today. We've been trying to work that in Seagate in Fremont in our lab. There has been some previous performance work done with fragmentation in Lustre. Those folks, I won't go into the details, but some of the work that's been done has been relatively incomplete. So it's not been an effective way of doing modeling. The first instance with Cluster Store, which is our Seagate product, a reported impactful fragmentation encountered at scale was dealing with metadata performance, with a metadata performance decrease. So Lustre can be affected by fragmentation on OSTs, just the metadata. We're not talking about bandwidth here. And dedicated resources have been allocated within Seagate to provide data collection for this problem. So this is kind of what we're dealing with today in Fremont. We've got a small test setup composed of a single storage enclosure, a small number of clients, Lustre 2, 7, and a variety of different utilities wrapped around this, and some Lustre client-side parameters you can see here. So we've come up with a nomenclature. We have a utility, and I can't go into all the details here because we're somewhat time limited on what we're using and how we're using it, but Matt mentioned Brinzel, which is our previous utility that I discussed a couple years ago for file system benchmarking. That's been modified to allow us to fragment the file system, doing a relatively non-deterministic fragmentation across file systems. So the way we view fragmentation today is different capacities of utilization and different fragmentation levels, non-deterministically, and different ways of generating fragmentation in a file system in the lab. Whether that's a Gen 1 non-deterministic homogeneous file system fragmentation exercise, or a multi-phase Gen-N pass, which is deterministic and heterogeneous, but it ranks from the extremely simple model to an extremely complex model. It just depends on the amount of time you want to spend in a lab studying this issue. So we have collected some data. The data is under analysis today. We have 2,240 result pairs for our first phase of fragmentation testing. That's composed of direct I/O writes and reads. And you can see here we've got different capacity levels we've run this at. We've got different 8 degrees of fragmentation, from 0 to 70% fragmentation in the file system in the lab, 7 different transfer sizes, mostly focused on direct I/O, and 5 iterational passes with each one of these tests. And all of this data is undergoing analysis. And so far, what I can say today is we are seeing some substantial impacts on Lustre at low percentage of utilization, depending on how the file system is fragmented. It's a work in progress. Analysis should be done by the end of the month. The full paper will be presented at LUG 2017. And for folks who can't make it, I'm pretty sure that eventually LUG papers will probably be posted to YouTube or some other internet site. So keep your eyes open if you're interested in this. If you've got questions about the work we're doing, here's my email address, both my ACM and Seagate emails. And thank you very much. Any questions I can answer right now? Yeah.
Hi there. Good, nice work. Is the tool specific to Lustre, or is it a general purpose fragmentation tool?
No, it's a general purpose fragmentation tool. It's written on top of POSIX IO. There's also an API I'm working on for cloud storage to play with cloud storage systems like S3 API. But right now it's focused primarily on POSIX.
Is it open? Can other people use it?
Today it
contribute to
is not open. Eventually we hope to open source it. It's been something I've had for a number of years, but it's based on both. It's a C utility, it's MPI enabled, so it's multi-thread. It uses POSIX threads based on top of the POSIX file system calls. So
Okay, because
it's kind of like, if you want to think of it as, one of my coworkers was one of the original authors of IOR. So this tool allows you to do intermixed block sizes, intermixed operations, a bunch of different things that IOR can't do for you today.
Okay. No, I see a lot of value in for the community as a general purpose tool. So.
Right. Okay, thank you. Unless there's any other questions?
Let's take.
Yep.
Just wanted to make sure I understood what low utilization means. Is it that the file system isn't terribly full yet? Is it that it's driving utilization low?
It is. We're doing it based on percent of utilization of total use capacity within the file system. So when I say 70% or 50% utilization, I mean the Lustre file system is showing 50% utilization. We could look at individual drives. We've done block traces, and I won't, obviously all this will be included in the final paper at LUG, But we've also done some work trying to determine how we take what we're learning in the lab related to capacity and fragmentation and mapping it back to the real world. Because it doesn't do us any good not to be able to understand how to take what we've learned in the lab and apply it to actual user sites, whether that's Seagate customers or someone else running Lustre. Other questions?
Just real quick, so I assume your testing that you're doing in-house is all on LZFS rather than ZFS? True?
No, today we're testing with LDiskFS. I hope to get to ZFS because ZFS, being a copy on write file system, has its own issues with regarding fragmentation. If you've used ZFS, you know it has an online defragmenter. I know ZFS is a very popular file system. Specifically at Lawrence Livermore, I know you guys at Los Alamos are using it as well, but it really initiated, ZFS underneath Lustre was really a Livermore project. And I would be curious to see how that responds to fragmentation, because I think in production use of ZFS, I think it's going to be a challenge if you start really heavily fragmenting your file system.
Can you give us a quick sneak preview of what the results look like so far in terms of degradation at low utilization?
So far, we've seen 20% bandwidth degradation at very low percentages of utilization, 30%, if varying your fragmentation model. I have a 3D surface plot that isn't complete yet that will be included in the final paper, which is basically it's three-dimensional. One axis is percentage of capacity you're running at. The other one is percentage of fragmentation as represented by the model. And the top end surface for the displacement is bandwidth available after 5 iterative passes. And it's basically a surface plot. And how that surface develops over those data sets will really determine how bad this problem can get for our simplistic model of fragmentation within the lab. Other questions?
Yeah, we'll follow up on David's question. Do you have any plans to publish it, and if so, where? So people, if they're kind of looking forward to
Well, the presentation will be presented at LUG in Bloomington in, I think it's the first week of June. And that will be posted. I'm pretty sure the LUG people, the Lustre user group people, will be putting all the LUG talks online for folks who can't make it to Bloomington. Not that Indiana is not an exciting place to be, but.
Very exciting. I went to Purdue, though, so
Yeah.
they're bad. All right, any other questions?
Thank you very much.
Okay, very good. Thank you. Let's thank John. Okay, let's go ahead and take a break. We'll take our break a little bit early. Peter should be here any second now, but this is a fine time to take a break. So there's